Select the major product of the following reaction. So if we take a look at what we're given here, we are starting with an ester. We're adding LDA, which is lithium diisopropyl amide. And what this is a really strong base. So there is the diisopropyl amide portion. It's got lithium as a counter ion. So this is a strong base. And what we've seen this used for is to irreversibly deprotonate something. And in the case of a carbonyl compound, when you deprotonate, you're deprotonating at the alpha position. So you're using this to irreversibly make the enolate. Okay, so where we're deprotonating is right here at this alpha position. Those are the most acidic hydrogens in this molecule. So we go ahead and redraw the structure of the diisopropyl amide. And so this can deprotonate at this alpha position. So that's what we're going to have in the first step. So we're taking an ester and we're completely converting it to the enolate. So now we have complete conversion to that enolate. And what we're adding in the second step is a different ester. So that tells us we're bringing together two different esters. This is a crossed Claisen condensation. So we've seen in the previous couple of videos a couple examples of self-Claisen condensation, where you used a weaker base and converted some of the ester to the enolate. But if we want to bring together two different things, we want to make sure that this ester does not undergo a self-Claisen reaction. So that's why we take and convert all of it to the enolate. If it's all converted to the enolate, then there's none of this ester left for the enolate to react with. And so then it doesn't have a choice. It has to react with the ester that we're adding in. So we're going to go ahead and we'll add in that other ester and use a different color just to emphasize where these pieces are. And then we've got a 3 carbon atom chain coming off this 1, 2, 3. All right. And so we can show this enolate reacting with this ester. And I'm not going to draw the entire mechanism here. We're going to take a shortcut. We're going to recognize that when this enolate attacks the carbonyl, it's going to push electrons up onto the oxygen. You get a tetrahedral addition intermediate, and then those electrons will come back down and kick off your leaving group. So we're going to shortcut this by saying the electrons go up, they come back on down, and they kick off the leaving group. But we are going to make our disclaimer that this is a shortcut and not a valid mechanism. But it is a handy shortcut if we're simply trying to get to the product. And so this is going to show us what we have brought together. So we've got the attacking enolate, and you can see that in the product because it's still going to have the ester portion. And so there's the alpha carbon. So I'm going to angle down from the alpha carbon, and we've got this benzene ring. So we'll just say phenyl. Here's our new bond right here between the alpha carbon and this carbonyl. And now what we're going to have left here is the ketone. The side that was attacked is no longer the ester because you lose that leaving group. So we're going to have the ketone, and let's count our carbon atoms here. We've got 1, 2, 3, 4 if we count from that ketone. So 1, 2, 3, 4. And that will be our final product. In case you're wondering about the other steps in the mechanism, you've also kicked off here, or in the reagents, OCH3-. So we've got some just acid-base chemistry that takes place. So this is going to deprotonate in between these two carbonyls. You can't stop that from happening. So that'll happen, and then you just have to add in that aqueous acid to put the proton back on. But in terms of getting to the product, this is all we need to know. So we want to take a look and see if we can find that product in our options. and it is right here in C. We can see that we've got, let's highlight these in the colors that we used. So this was our attacking enolate. You can see that CH2 right there, or CH I should say, sorry. And then we come down, we got this phenyl ring. And then we can see the side that we attacked here. So we can see the ketone, and that's 1, 2, 3, 4 carbon atoms. So that is our right answer.